Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology in the subject of Mathematical Methods of Physics 2 with the course code PHY 222. We are at the lecture number 9 and the topic is linear first order differential equations. In today's lecture, I am going to explain to you that what are the linear first order differential equations and their methods of solutions. So let's start with the definition of a linear first order differential equation. So as you can see that the word linear over here, which means that we will be having either the variable involved or its first order derivative, and we will not be having any second order derivative. So it contains, as I have defined over here, the first order derivative but no higher order derivatives. For example, the second order derivative or third order derivatives are not involved in these equations. These are kind of simplest equations where we just have the linear power, that is the first power or the first derivatives involved in the equation. So the form looks like this. So it's the general form which you see over here. Here the first term contains y prime. By y prime we mean that the derivative with respect to x, because here y is actually a function of x. So if y is a function of x, and then by y prime we mean that it is dy by dx, that is derivative of y with respect to x is involved over here. So you see that the first term contains only the derivative and which is only one derivative, that is d by dx of y, and no higher order derivatives are involved in the first term. Let's come to the second term. In second term you see that we have y, even no derivative, even first order derivative is not here, and we have a constant, it's the function p multiplied with the y, and this function p and also this function q, which we will talk later, are functions of x, so they depend upon x. So this is a function p multiplied with a y, so this term also has no higher derivatives, even it does not has any first order derivative. And then it is equal to q, it is another function over here of x, and again it has no y or first order derivative or even higher order derivatives. So this equation is a truly linear first order differential equation. Such equations are used in physics to model many physical situations and problems. Later in the lecture I will give you an example of it in radioactive decay, where this type of equation will be used to solve the radioactive decay problem. Okay, so now you know that what is first order linear differential equation. It has something which involves the only one derivative of some variable, in this case it is y, and then the linear power of it multiplied with some functions. So we can transform this equation into even a simpler equation if we have this q function equal to 0. So there is a particular choice that when the function q is 0, then this equation actually transforms even into a more simpler form, as you can see over here. We are considering this situation to illustrate the solution of such equations. Later on we will be considering when q is not equal to 0, but to begin with I am giving you the simpler version of it when q is equal to 0. So when we consider that q is equal to 0, now it is sort of equation which is actually separable, where we can separate variables. And how we can do this, you can see over here. Or first let's write it in a more explicit form by writing y is equal to d by dx. So d by dx into y will be equal to minus py. So this equation gets into this form, where we have taken py to other side of the equation of equal sign, and it therefore it got the negative sign. So now this equation is equal to dy by dx is equal to minus py. And this equation is, as you can see clearly, is a separable equation, where we can separate the x and y variables. And how we do this, first of all, you can see that I have brought y from in this equation. So this you can brought this y, bring this y variable to this side of the equation, and take this dx to the other side. And since p is a function of x, so this p is actually a function of x. So then right side will contain variables or a function of variable x only, and this left side will contain the variable y or a function of variable y. So here you can see that the left hand side of this equation now becomes dy by y, and the right side is equal to minus p dx. So you have seen that when we put q is equal to 0, then this equation is actually a separable equation, where we can separate variables to the left and right side. Now in order to solve this equation for y, we can take the derivative of it, and that will be transformed into natural log of y, or we can integrate on both sides. If we integrate on this side, we will get natural log of y. This will be equal to the integral of p dx, and this is the constant of integration. And even we can make it more simpler by taking this natural log over the other side, or taking the exponential, which will cancel out natural log over here, and we will get e, and this whole term here you can see minus integral of p dx plus c exponentiated over here, and then this can be written as equal to a into e raised to power minus integral of p dx. And you can see that this c, the integral over c, is separated and put into the definition of this constant a, as I mentioned here, that a is equal to e raised to power c. So now you have seen that it's a kind of solution to that equation, where q was equal to 0, that we have got now y is equal to a into e raised to power minus integral of p dx. So although we have already got this equation, as you can see, but before writing the most general solution of first order linear differential equation, I would like to put it in a more convenient form. And for this we get into a simple notation, where let's call integral of p dx equal to I. This is I, and this symbol I also has meaning. You will see that why we use I as a symbol over here. It has a special meaning there. And this integral of p dx, let's call it I. And then since we also have the derivatives involved, so let's derivative of I with respect to x is equal to p, because if you differentiate on both sides, the integral goes away, and you get p is equal to di by dx, and from this definition. Then the solution we have found on previous slide is now put into this form, which you can see is a very simpler notation, that y is equal to a into e raised to power minus I. So it means that the linear first order differential equation, where we put the function q is equal to 0, could be written into very simple form. Their solution can be written into very simple form, that is y is equal to a into e raised to power minus I, where I is given into this definition. So now it's time to solve and to give you the general solution. And for this, first make this more into convenient form. Since you can see over here, this e is y is equal to a into e raised to power minus I. So let's take this e raised to power minus I onto the other side and put it like this: y into e raised to power I is equal to a, where a is that constant. And if we differentiate this with respect to x, because y is a function of x, and all of them have are containing some terms which are functions of x. So if we differentiate this equation, what we will get is, as you can see on the left hand side, the derivative of this term, since it's there are two terms on the left hand side, y and e raised to power I, which are both functions of x. So if I apply the rule for the derivative, then it will be y prime, that is the derivative of y first, and e raised to power I, and plus y into derivative of e raised to power I will be equal to e raised to power I, and further derivative of I will be di by dx. So here you see now that in this equation, after the differentiation, this e raised to power I is in the both terms, as you see over here, and this di by dx, which we have defined before, is equal to p. So this is equal to p, and if I take e raised to power I common from both terms, because it is included in both terms, so we can just take the common out. So we will be left with y prime plus py, and this e raised to power I is called integrating factor. So this is the integrating factor. Remember that I told you that this I is used because we will use it as a this I symbol is used because of the integrating factor. So now we see that the solution coming in the form that we are multiplying e raised to power I with y prime plus py. Remember, this was the sort of equation we had initially when we put q is equal to 0. So we were left with y prime plus py is equal to 0. So you see that left hand side of this equation is getting multiplied with some kind of a function. We called it integrating factor. So when you multiply the equation with the integrating factor, then you get some solution of it, or you can solve it. Okay, so the final equation which results from this differentiation is of the form q into e raised to power I. So let's call it q, because this is now in the general case, because till that we have done the case when q was equal to 0, but this thing is in the case when q is not equal to 0. So when q is not equal to 0, then q is equal to actually this thing over here. Q is equal to this thing. So therefore we can write this equation as q is equal to ei, and this is now more generalized form where we are multiplying e raised to power I with the function q. And now we are able to write the general solution in this form. So this is the general solution of the linear first order differential equation, since y multiplied by e raised to power I, that is the integrating factor, as you have seen, was equal to the integral of q into e raised to power dx plus constant of integration, or where I is if you remember that I is equal to p dx. So our general solution y is now, if we take this e raised to power I, that is integrating factor, on the other side of the equation, e raised to power, it will become e raised to power minus I, and q e I dx. This is the first thing, and if we substitute back the c value, then and multiply this e raised to power minus I with this one as well, so we get c into e raised to power minus I. So you see now this is the most general solution we have, and for the first order linear differential equation. and we now just have to use this integrating factor, and if we know the q, we can solve equation very easily. So in this first part of the lecture, I have given you the general definition of linear first order differential equation. So these are the equations which involve first derivative in one of their terms, and if we want to solve them, we can solve them with the help of integrating factor. So we have to determine that what is the integrating factor from the function p involved there, and once we know the integrating factor, then we can easily multiply out the rest of the equation, which is equal to q, with the integrating factor, and get out the solution. And now it's time to give you examples of this type of equation and its solution. So in example 1, we will solve this equation. So now first look at this equation. This is equal to 1 plus x square into y prime plus 6xy is equal to 2x, and this is, you can see, is a first order linear differential equation. So the first term has y prime, which is remember is the derivative of y with respect to x. So so it is first order derivative, and the second term contains y, and the 6x, now you might be thinking what it is, so we can identify it with a p, and this 2x with a q. So you see that this is sort of, although we will simplify it more, and the definition of p will change, but at the moment you can see that it's sort of this equation. So let's put it in a slightly different form to make the definitions of p and q easily seen. So you see that this can be written as y prime and 6x, because I have divided the full equation with 1 plus x square. This was the coefficient over here, 1 plus x square. So if I divide the whole equation with 1 plus x square, so what I will get is y prime plus 6x over 1 over x square y is equal to 2x plus 1 over 1 plus x square. Now it is more clear that what is p and what is q, and I show you there that okay, before telling you what is p and q, let's have the definition of integrating factor I, and this will be equal to, this is p dx, because this is p, so this is p dx, and I can write it as an integral. Remember that I was equal to p dx integral, so this is p integral dx, and you can simply calculate this, it's not very difficult, equal to 3 natural log of 1 plus x square. And then if we exponentiate it, e raised to power, because the integrating factor is actually e raised to power I, so we will get e raised to power 3 natural log of 1 plus x square, which can be written as 1 plus x square raised to power 3. So you've seen that we got the e raised to power I here, and once we have e raised to power I, as I okay, so let's go back, and as I promised you to show you the p and q here. So this is the p, as you can see, and it is a function of x. So this is p, although, but this is a function of x, so it's actually p of x, and this is q, and again this is a function of x, as you can see. So this whole thing over here is q, and this whole thing over here is p, and they are functions of. So this equation is basically y prime px is equal to qx. So this is what equation p is a function of x and q is a function of x multiplied with a y here. So this is this equation written over here, and we want to solve this equation, that is to get the value of y. But since we know how to do it, we have to find out the integrating factor, which we have already done, and now we know the general form of solution, which is this one, that is y into e raised to power I. So y into e raised to power I will, now you know what y is, and what e raised to power I is, we have already find e raised to power I, and we also know the y. So we can simply now simplify this term, which is cancelling out one power. You will get this thing, and if you make the integration, this is the integration, a simple integration by power rule, and you get this thing, and from here the y is equal to 1 over 3 plus c into 1 plus x square into 3. So you see that how easily we have solved this equation. So in this first equation, although there was in this first example, although there was no physical understanding involved, but I have shown you that how different steps can be made and how integrating factor can be found, and then multiplying this integrating factor with the equation, we can very easily determine the solution. So now it's time for example number 2, where we will be considering a physical situation now, and we'll model this with the linear first order differential equation, and then we'll solve it, and that's physical problem, and we'll see that how easily it is solved when we model it with this type of equation. So let's consider a radioactive decay problem, where let's say a radium decays to a radon, and which further decays to polonium, and if at time t is equal to 0 a sample is pure radium. So the question is how much radon does it contain at time is equal to t. So this is a problem, as you can see it's a physics problem, but in order to answer this question, that is how much radon does the sample contains at time is equal to t, we model this problem with the help of the linear first order differential equation. So let call n naught is equal to number of radium atoms at t is equal to 0. So let the number of radium atom present at initially, that is at time t is equal to 0, were equal to n naught, and n1 is the number of radium atoms present at time t, and n2 are the number of radon atoms at present at t. Because it's a radioactive thing, so we have a number of atoms present of radium sample, which is the parent nuclei, but then it decays into polonium, into radon, and radon is also a radioactive and it decays into polonium. So we have made these simple definitions of n0, n1 and n2, that is a number of radium atoms at t is equal to 0 and t, and the number of radon atoms at t. And let's also define lambda 1 and lambda 2, which are the decay constants for Ra and Rn, that is radium and radon. So now we have defined all the parameters needed to transform this statement into a differential equation. So we can do this as we know that the decay rate of n1 dn1 by d2 is equal to n1, because it's proportional, number of atoms decaying are proportional to the number of atom present. So remember, in radioactive decay, this is a law of radioactive decay, that if there are more number of atoms present, then the decay is faster, and if the number of atoms are less, then decay is less. And it also depends upon the type of the atoms, the type of the atom present there, which is lambda 1. So you see that in the first atom the decay rate can be written like this, and if we want to find out the value for n1, we have to integrate this, and integrating on both sides we get the n1 is equal to n naught, where n naught are the number of atoms present at t is equal to 0. So, and similarly radon is also decaying, so we can write dn by dt is equal to lambda 1 n1 minus lambda 2 n2, because there is a difference of number of atoms present of radium and radon, or taking on to the other side and also integrating, we can get the value for this, that is lambda 1 n naught e is for lambda 1 n1 we get lambda 1 n naught e is for minus lambda 1 t, because if we solve it we get lambda 1 n1, and n1 we already know is equal to n naught e is for minus lambda 1 t. So putting it over here, so this equation is transformed into this form, and the integrating factor in this case, or not the integrating factor, but I is lambda 2 into t. As you can easily see, we can write it like this, and then n2 e raised power lambda t2 into this integral, just making the substitutions for e raised power lambda 2 t. We can write it into this form with the constant of integration, and then solving this integral, putting these exponentials together, as you can see easily, and solving this integral. This is the final form we obtain. And if in the situation when lambda 1 and lambda 2 are not equal, we get this is equal to this derivative, as you see over here, then this is equal to 0, and we get the value of c. We have determined the value of the integration constant, and with this the n2 is completely determined, and this is the expression for n2 in terms of the n0 and also the two constants, radioactive decay constants. So these are the references, and in order to give you the summary of today's lecture, what we have done is to discuss the first order linear differential equations. Those are the equations which contain the first order derivative terms, but they are linear. So first of all, we have developed the method of solving these type of equations, and important thing was the integrating factor, to how to find out the integrating factor. Once we have determined the integrating factor, we were able to write out the general solution. And later then I gave you the two examples. In the first example, it was just the steps to show how to solve such equations, and then in the second equation we have considered a physical example of radioactive decay, where you have seen that we have determined the radioactive decay. We have modeled it with the linear first order differential equation, and then we solved it easily because we knew that how to solve these equations. With this, I thank you all.